Hi, I'm Adil Al-Mumni, Rheology Product Manager at T-Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging windows to your liking. You can resize the video and slide windows independently from one another by clicking and dragging the bottom right corner of each window. If you get disconnected at any time, please use the instructions you have received to log back in. You can access several different content windows by clicking the widgets at the bottom of the screen. These include speaker bios and additional file downloads. If you need help, click the question mark widget. Please ask any questions that you may have during this presentation by submitting them through the Q&A window. We'll answer as many of these as possible at the end of the webinar. Our guest speaker today is Professor Norm Wagner. Professor Wagner is the Alvin and Julia Stiles Professor in the Department of Chemical and Biomolecular Engineering at the University of Delaware. He leads an active research group in the field of soft matter science and engineering with focus on the rheology of complex fluids, neutron scattering, colloid and polymer science, applied statistical mechanics, nanotechnology, and particle technology. His awards include the 2014 Bingham Medal of the Society of Rheology and the IACHE Baron Award in 2013. He's a fellow of the Neutron Scattering Society of America. He was awarded the Sipple Award in 2002 by the U.S. Army for his development of shear thickening fluids for novel energy-absorbing materials. We're honored to have Professor Norm Wagner speaking with us today. The title of his talk is An Introduction to Colloidal Suspension Rheology. Norm?
Thank you very much, Adil. Thank you for the opportunity to be here to talk about colloidal suspension rheology. This course is based on my book, Colloidal Suspension Rheology, published by Cambridge University Press, published with Jan Mavis, my co-author from KU Leuven. And there's a website where you can find some more information there about the book and about some questions and answers. Now, the objectives of today's webinar is to provide you with a qualitative introductory understanding of the various phenomena that contribute to the rheology of colloidal suspensions. We're also going to make an introduction to basic scaling relationships and quantitative laws to predict the basic rheology of such systems. The outline of today's course will be, again, a little bit on colloids and colloidal suspension rheology, some background information. Then we'll talk about the types of interactions. This includes hydrodynamic interactions as well as colloidal interactions. And then we'll go through the rheology of stable suspensions with the time we have. And then I'll give you a summary and some places where you can get further information. To sort of introduce that, there is a short course that's based on this book, and this webinar is an introduction to that will be taught at the Society of Rheology meeting that takes place in Philadelphia in October. And I'll put this slide back up at the end of the seminar. So the types of colloids that you typically see. This is an SEM image of colloidal silica, typical spheres, less than a micron in size. This is a polymer, in this case a dendrimer in solution. That's also a type of colloid. We also see many different types of minerals in practice, such as acicular precipitated calcium carbonate that's used in materials such as paper coatings, to fumed silica, to faceted materials like the kaolin clays, platelet-like materials, montmorillonite in that, silicon carbide whiskers. There's a wide variety of different structures, the typical images you can see there, that are also colloidal. And finally, there are biological materials, in particular proteins that we run across every day. These are also colloidal, but they're also complicated. They're sometimes spherical, sometimes not, but they also have very complicated surface interactions, and we'll come back and talk about surface forces shortly. Now, the colloidal world is a little bit different than our macroscopic world, in particular because of the large amount of surface area that such fine particle dispersions have. That surface area leads to the presence of comparatively long-range electrostatic forces. Shown here is an image of a colloid or a cartoon, and you can see a carboxylic acid group on the surface. Often that's put on chemically, or it could be adsorbed ions coming out of solutions, such as in the case of minerals. That leads to an electrostatic potential. You see the graph in the lower right, you see the red curve, and that's showing you the range, if you will, of the electrostatic potential that's around these spherical particles that will cause them to interact even if they're not touching. Finally, colloids also have Brownian motion, right? That's a very important thing that we need to talk about as well because they're so small. Now, there's a basic kind of scales for things that we need to know up front to understand or have a sense of the rheological properties of colloids. The first of these is sort of the energy scale. If you go back to your physical chemistry class, you'll perhaps remember the ideal gas law, where RT, or the gas constant times temperature, sets the energy scale for a gas. Well, R divided by Avogadro's number is known as Boltzmann's constant, K, so that's per molecule instead of per mole. And KT sets the energy scale. And as you see here, typically at room temperature, that's on the order of 10 to the minus 21 joules, which is a very small amount of energy. But if you put that energy into a colloid, which is a very small particle, that leads to a characteristic stress, that is the energy divided by the volume of the colloid. That's on the order of about 1 or 1/100th of a Pascal, depending on the particle size. The smaller the particle, the larger that energy scale is, but you should remember it's on the order of something less or greater than a Pascal, between maybe a millipascal up to a kilopascal. Now, that energy that's put into the colloids moves them around. We also have a KT of thermal energy, but we're big, and so that doesn't push us around. But for such a fine particle in solution, it'll make it undergo Brownian motion. And if you balance that against the Stokes drag, that is the Brownian force or the Brownian energy pushing the particle around, balanced against the Stokes drag that's resisting that, you end up with the Stokes-Einstein relationship that I'm sure many of you are familiar with, that gives us the basic rate of diffusion of a Brownian particle. And as you see the equation at the bottom, the Stokes-Einstein-Sutherland relationship, the diffusion coefficient is KT divided by the 6 times pi times the viscosity of the solvent and the particle size. So when you have very small particles, you can get a fairly large diffusion coefficient. Now that leads to some very interesting things. Remember, Brownian motion is named after Robert Brown, who was a 19th century botanist who first observed Brownian motion in a microscope. And what he observed was a colloidal particle dancing around or moving around in solution. That occurs because of the thermal energy of the particle that's imparted to it by the collision of the solvent molecules, as you can see on the graph here on the left. The Brownian motion looks like a random motion, right? The particle just moves left, right, back and forth. And you can get a rough idea of calculating how fast that diffusion is by putting in some typical numbers, such as the viscosity of water, the temperature, room temperature, Boltzmann's constant, which is known, and a particle size on the order of a micron. You end up with a diffusion coefficient that's 10 to the minus 13 meters squared per second. Now that may not really mean much to us, but you can calculate a time scale that's important for the rheology by using that number and the characteristic particle size, which again is a micron, to calculate a characteristic time scale for Brownian motion. That time scale shown in the bottom equation, a squared divided by d naught, ranges from about 5 microseconds for very fine colloidal particles, ones that are only a few nanometers in size, such as a protein, up to about 5 seconds for micron-sized particles, which are the upper end of the scale. That's important because that time scale is relevant for setting the characteristic shear rate. So we can make a dimensionless shear rate known as the Peclet number. That's defined in the first equation on the left, where we take the ratio of the shear rate to that Brownian diffusion, the rate of diffusion, okay, which is 1 over that time scale. And you can see it strongly depends on the particle size. It goes like a cubed. If you take rheological data, and we'll talk more about typical data, but as shown on the graph here, a dimensionless viscosity divided by a characteristic stress ratio or Peclet number, that will undergo shear thinning, and the characteristic rate or shear rate where that shear thinning happens is 1 when calculated as a Peclet number. So again, the balance of the Brownian time scale against the shear rate tells us whether the shear is fast or slow. Another way to do experiments, of course, is to use a stress rheometer, and then you'd be measuring stress, which is actually what's plotted on that graph. And we could do the same thing. We could say there's a characteristic stress, which we just talked about, right? That's KT divided by the particle size cubed, right? The energy per volume. And you get a very similar relationship, also a Peclet number, based on stress instead of shear rate, that tells you whether the stress you're applying to the suspension is low or high. Okay? Now, there are other forces, as I mentioned in the beginning, in the colloidal world. Very importantly are the electrostatic forces. They lead to stabilization, generally, of the particles. That's shown here in the plot, where you see the colloids, which are the gold spheres, having a negative surface charge. Of course, there must be the positive counterions out in solution, plus any other salt, and those are the plus-minus ions you see swimming around in the liquid, which is given as the blue color. When 2 colloidal particles come close together, those double layer, it's called, overlap. And what you see is, of course, an electrostatic repulsion, because 2 like-charged objects like to repel each other due to the overlap of that electric field. But there's also an effect, essentially, due to the osmotic pressure that's created by having a concentration of those counterions in between the 2 gold particles. Either way, that leads to a relatively large force that tends to stabilize and keep the particles apart and keep them from aggregating. Now, what causes the particles to aggregate? Well, if you go back to your physical chemistry class back in high school or in college, you'll remember the Vander Waals fluid. And you'll remember what Vander Waals got the Nobel Prize for was essentially understanding that all matter, atoms in a gas or in a liquid, will attract each other. And that attraction comes about because the electron clouds in those atoms are fluctuating, and they create a dipole instantaneously. And that dipole radiates an electromagnetic field, and that interacts with the other atoms around it in a positive way, such as to attract things. That creates the attraction that leads, for example, to water forming a liquid, okay, and ultimately crystallizing. In the colloidal case, colloids are made up of atoms, so those atoms polarize the atoms of another colloid, and that's illustrated in the cartoon that you see here. So the blue sphere, the atoms in the blue sphere are having fluctuating dipoles due to the motion of their electron clouds. That polarizes the electron cloud in the yellow sphere in such a way as to be an attraction. That attraction is very strong when the particles are close together. In fact, that's what keeps matter together in the first place. The coefficient of that potential that results from that interaction is known as the Hamaker constant. And that Hamaker constant, A, is a strong function of the materials. So once we pick, for example, kaolin clay and water, that sets the value of A, and you can go look that up. Okay? So if we take the repulsion that we talked about and we add the attraction to it, we end up what's known as the DLVO potential. And that's the classic potential that's used to describe classic colloidal systems. And that will be important for the rheological properties of our materials. The DLVO potential is named after Deriag and Landau, who were two Russians, who at the same time as two Dutch scientists, Verwey and Overbeek, developed this basic theory. Of course, this happened during World War II, and the two parties didn't know about the other one's work till after the war. And in recognition of all four scientists, we call that the DLVO potential. That is illustrated in the following plot. So let me walk you through this plot a little bit so you understand what's going on. So we have two colloids, the blue spheres that you see on the plot there, and they are separated by some surface-to-surface distance h. That's what's plotted on the x-axis. On the y-axis is plotted the interaction potential. Now, remember the electrostatic, the overlap of the electric double layers around the particles. That's the dashed blue line that you see that starts in the upper left corner and comes down smoothly to zero. That has a finite range that's fixed by the pH and salt of the solution and the charge on the particle surface. The Vander Waals attraction is the reddish dashed line that you see starting in the lower left corner and gradually coming up below the x-axis. That's of much longer range. So when the two particles are very far apart, they don't see each other. Their interaction potential is zero. But they start to feel, as they come closer and closer together, that is moving from right to left across the graph, they start to feel an attraction. The overall potential that they feel is the sum of those two. That's the DLVO, and you see the red curve. Now, that red curve has a very non-monotonic behavior, right? There's a minimum, which we call the secondary minimum. That secondary minimum leads to flocculation in colloidal systems. That is, the particles aren't touching, but they're attracted to each other. If that's on the order of the thermal energy, KT, remember that critical energy scale, then the particles will start to stick to each other for some amount of time. They'll have some lifetime, and they'll form flocks. Those flocks can lead to structure and interesting rheological behavior, such as viscoelasticity and yield stresses. If the particles get closer together, they'll start to feel a stabilization due to the electrostatic force that will be an energy barrier, if you will, to keep them from actually touching. But that energy barrier has a finite maximum, and that's labeled as the stability maximum. If that stability maximum is high enough, particles will never get over that barrier. But in many cases, it's not that large. It's only on the order of 5 or 10 kT. And in such cases, with time, slowly, occasionally, particles will jump over the barrier and stick together because they'll fall into what's labeled as the primary minimum. The primary minimum is where the particles would touch if there's nothing to prevent that from happening, such as a polymer or a surfactant. We'll talk about that briefly. Anyways, if I apply shear to a stable suspension that might not be able to get over the stability maximum, and I shear it, it might be shear sensitive such that I push it over that barrier and the particles aggregate. Once particles are in that primary minimum, it's virtually impossible to pull them apart. You might have to use sonication, you might have to shear them at incredibly high shear rates, or they may never come apart. Finally, we could add polymer, and that's often done to prevent particles from coming into that primary minimum. However, the addition of polymer is not so easy. This little cartoon taken from a common textbook from Hymans and Rajagopal sort of illustrates the effect of adding polymer. So I start with two particles in the upper left of the boxed image there, and I add a little bit of polymer that sticks to the particles. This is typically what you do when you do water treatment, right? To flocculate fines and pull them out of solution. What happens? You get bridging flocculation. If I add enough polymer and shear it a little bit or sonicate it, that polymer will coat the particles and actually stabilize them, and they'll be stable again. If I add a little more polymer, I get something called depletion flocculation. We won't talk about that in detail, but that requires that there be free polymer in solution that drives the particles together and creates a net attraction between them. And finally, if I add even more polymer, I'll get depletion, or I'll get stabilization again. So polymer can either aggregate or create stability, or do the opposite, right? Or create, again, an instability in the system, and it's complicated. Now let's back up. If I take just hard spheres and I take away the electrostatics and I don't have polymer and I don't have any attractions, I have just hard spheres. Think of billiard balls, but billiard balls that are moving around due to Brownian motion. They already have a phase diagram, and we need to understand that to understand the rheology. So what's shown here is a typical phase diagram for this system. On the left axis is just a cartoon. There's no temperature scale to the hard sphere phase diagram. It's athermal. It doesn't depend on temperature, but it does depend on the volume fraction. So going from left to right, we start with just a few particles in solution, and they just move around by diffusion. If I add enough particles and I get to 50%, they'll undergo a crystallization phase transition. And at 55%, you have a pure crystal. And that can go up to 74% where you have maximum packing. Think about a stacking of oranges, or if you will, in the grocery store into a nice FCC lattice, right? That's the maximum packing that you can get. However, many colloidal systems the crystallization is slow, because on Earth or with gravity, and with many systems, crystallization takes a long time. So as we concentrate the system, we often end up with a glassy state at high concentrations. Around 57, 58%, we get a structure that isn't crystalline, but still has solid-like rheology. And that's going to be really important for us to understand when we talk about the rheology of hard spheres, that we have a liquid state that can exist up to about 57%. And after that, at least for the zero shear viscosity, we're going to see something that's solid-like and not liquid-like from there on. Now, finally, if I add the attractions, okay, then interesting things can happen. And you know that from your basic physical chemistry class. If you think about water vapor and you cool it down, it rains, right? It's liquid water, and ultimately can also crystallize, right, as ice. And so on this graph, I again have volume fraction on the x-axis, the volume fraction of the particles, but on the y-axis, I have the temperature, a dimensionless temperature scale. So the hard spheres are essentially at the top. That is, they're either liquid or they undergo a phase transition, which is the gray region at the top of the graph, or they form a glass, which is the RDG, repulsive-driven glass line that you see there. Okay? As I add attractions, though, the particles become sticky. They begin to cluster with each other. And what you see then is something called the gel line. Those are the green points there. They're actually experimental data given in the reference that's shown there by Eberle et al. And there's a critical point, and below that you get a phase transition where the system actually phase separates into a colloidal gas, which is just a dilute colloidal solution, in equilibrium with a colloidal liquid, which is a liquid-like, dense packed particle suspension, droplets of that form, and they're just like rain, if you will. Now, the typical structures that we see when we add attractions, we go from a nice dispersed structure to something that's fractal-like and forms a network and a gel, and that'll have a very interesting rheology all of its own. At a higher concentration, we can't really form fractals because these fractals, after a few particles aggregate, they bump into each other and form a solid-like network. We call that a gel. And finally, at really high concentrations, we once again have a glass, where you really can't talk about any fractality. Every particle is sort of caged in by its neighbors, and that's shown in the cartoons there. Now let's get to some rheology finally, okay? So we take some colloids and we put them in water, and we end up with some interesting curves that we could take at the different volume fractions as a function of the shear rate, or the shear stress that we put on the system. I've selected a very nice graph here. This is a paint surrogate, a colloidal suspension from Martin Lown at BASF Corporation, published in the 1980s. And it very nicely illustrates the rich behavior of even just the shear viscosity of a colloidal suspension. Again, water is the lowest one, labeled 0. That's the medium that the colloids are in. And you can see it's Newtonian. That is, the viscosity is independent of shear rate or shear stress. As I start to add particles, you can see the different volume fractions labeled there. More and more particles lead to a higher viscosity, and that's a logarithmic scale. Eventually, though, something interesting happens. I start to see what's called shear thinning. That is, the viscosity goes from a certain plateau value to another plateau value that's lower at a finite shear stress. And guess what? The shear stress where that happens is on the order of about a Pascal. And that's what we talked about before as a characteristic stress for colloidal suspensions, right? And that's where you would expect Where is the stress large or small? Well, it's when it balances that characteristic stress, which is on the order of a Pascal or so. And finally, if I start adding enough particles, you can see that I lose the zero shear viscosity. The curves don't go there anymore. They don't plateau out. In fact, I can't measure it. What I start to measure is what's called a yield stress. In a yield stress situation, the viscosity is essentially infinite at rest. Okay? But as I apply a flow, I see a shear thinning effect. Now, at high shear stresses, something really interesting starts to happen, and that's known as shear thickening. And what you can see here, which is very undesirable in paint formulations, is that the viscosity starts to go back up again at very high stresses, and we'll talk about that next. What's important to recognize is that for hard spheres, theory and scaling relations tell us that the viscosity should really be a function only of the volume fraction and the stress that's applied on the system. Now, we can do another type of rheological measurement on colloids that isn't just measuring the shear viscosity. We can do small amplitude oscillatory shear. That's often done in polymer systems to characterize a plateau modulus and a relaxation time. And you could do the same thing as for colloids, as shown in this plot here. In the lower right, what you see is the applied strain and strain rate. That's applied by the instrument in the rheological test. What we do is we separate out the stress response, which is shown in the lower right graph, as stress versus time. And you can see we could separate it to a part that is in phase with the strain rate, and that's known as the viscous modulus, and a part that's in phase with the strain itself, and that's known as the elastic modulus. Think of a spring-like behavior. On the left is some classic data from Shikata and Pearson on a colloidal silica, concentrated colloidal silica suspension, and that suspension is still liquid-like. And it looks kind of strange, maybe, to those of you who've seen polymer type of behavior for polymer solutions or melts before. And what's really particular is that G double prime is very large, the viscous modulus, and it's always above G prime, which is the lower curve there. And in fact, G double prime is really very large and goes up in a linear way with frequency at high frequencies. And that's characteristic of colloidal suspensions, and it comes about because of the strong hydrodynamic interactions that are always present in colloids, which are generally not so important in polymer solutions and certainly not present in polymer melts. If I take that plot, as Shikata and Pearson did, and I subtract off that high frequency viscosity times the frequency itself, that is the high frequency modulus due to the hydrodynamics, then the main plot that's shown there is actually much more characteristic of a viscoelastic kind of response that you may have typically seen. For reference, I've sketched the Maxwell model that many of you probably are aware of, the G prime shown as the blue and the G double prime shown as the red in the lower right curve. And you can see the general features are shown also by the colloids. Now, where's this viscoelasticity coming from? It's coming from the Brownian motion, right? There's a characteristic time scale of the colloids moving around that sets whether the frequency is high or low, right? Is the frequency high or low? We can make essentially a Peclet number based on that. So we can take the data and we can subtract off the hydrodynamic effects, and we're left with the contribution due to Brownian motion to the viscous and the elastic moduli for a colloidal suspension. And this is for a liquid. Now, if I take those hard spheres and I concentrate them further, remember what happens. If I don't allow them to crystallize, maybe they're polydispersed, maybe I do this quickly, then I see a glass. And a glass is a very interesting material because it's solid-like, but it has liquid-like behavior. And that's often used in material science to form some very interesting materials. In terms of the colloidal glass, the particles are still not touching. They're still moving by Brownian motion, but their motion is strongly constrained by the presence of the neighboring particles. That's sort of illustrated by the cage of the blue particles surrounding the gold particle that you see in the image there. So if I look at G prime and G double prime, which have been normalized by the authors, this is a nice paper in the Journal of Rheology by Miriam Siebenberger and co-authors, as a function of Peclet number, that is the frequency, the Peclet number based on the frequency, so that's the dimensionless frequency, you can see a very different behavior. You see what looks like a plateau modulus, the solid symbols, and you see that the loss modulus now, G double prime, is less than G prime, and it shows a minimum. Now, if they could have gone to low enough frequency, they might have seen a crossover. Okay, the data suggested the theory that's through there, the so-called mode coupling theory, which I'll talk more about in a minute, does show a crossover. That crossover gives you a characteristic relaxation time. That relaxation time is the alpha relaxation time for colloids, and that's related to the time it takes for that gold particle to essentially escape from its neighbors, right? Get out of that neighborhood of the blue particles around it. This characteristic relaxation time to become a liquid. So this is a glass, but a glass will slowly creep and flow if you wait long enough, and that sets that time scale. The other relaxation time is the minimum that you've seen in the open symbols, the G double prime curve on the right, label it as tau b. That's called the beta relaxation time. And that has to do with the diffusion, if you will, diffusive motion of that gold particle in the cage of its neighbors. How long does it take for that particle to explore its neighborhood? So again, by doing a small amplitude oscillatory shear measurement of a colloidal suspension, in the glassy state, I can learn something about those two relaxation times. On the left is the flow curve that corresponds to that same sample, and where the authors have plotted the experimental data there, and they've indicated what looks to be like a yield stress. That is, this is stress versus shear rate, stress versus Peclet number, and the stress doesn't go to zero at zero Peclet number. At least the model shows that it sort of extrapolates to a finite value. Yield stresses are tricky to measure in colloidal systems because they're often not that large, and it often matters how long you're willing to wait and the pre-shear conditions and the aging of your sample, but nonetheless, there's an apparent yield stress in this material. That is, it doesn't flow under its own weight at rest. The model that goes through the shear data and the model that goes through the viscoelasticity data is known as the mode coupling theory, and all that name really tells you is that it's based on the idea of this caging model for the colloidal suspension. And we'll come back to the mode coupling shortly. Now, what we've seen so far is then, just looking at experimental data and thinking about the system, is that there are fundamentally two types of colloidal interactions that are going to strongly affect the rheology. First, we have hydrodynamic interactions. And where do those come from? Well, we have a solvent. We have solid particles in it. So as soon as I shear a colloidal suspension, the particles, they don't deform, right? And so the fluid has to flow around the particles. Furthermore, if I move a particle, right, by Brownian motion, that particle has to displace the liquid to move, which means it creates a flow field, and that flow field interacts with the other particles. So these are very strong interactions propagated by the presence of the solvent. They are not there in many other systems, such as atomic systems, where you have a vacuum between the particles. So they're essentially characteristic of colloidal suspensions. They're always dissipative. They always cause an energy loss. That means they lead to G double prime contributions and not G prime contributions. They scale with the medium. They depend on the viscosity, if you will, of the medium. So if that's temperature sensitive, these will be temperature sensitive. It depends on the volume of the solids that are there, and it depends on the size and shape, and particularly the shape and the polydispersity of the system, and in proportion to shear rate. That is, the forces are direct proportion to shear rate. So if I turn off the flow, these go to zero. Okay? And that's one way to determine them. The colloidal interactions we've introduced, on the other hand, are very different, right? They tend to scale with either the surface area or the volume in the case of the Vander Waals forces. They depend on the particle, the medium, they depend on the pH, the salt, and the other features of the solvent that the particles are in, and the conditions that you've made on the surface of the particle. And these colloidal interactions are really what set the thermodynamic phase behavior as we've seen in the system, okay? Both of these types of interactions contribute to the rheology, but as we've seen, differently. Now let's talk a little bit more about that. So what I've plotted here are the best theoretical data that we have from simulations, Stokesian dynamic simulations. This is from the work of John Brady. And for reference, I've shown you that little plot from Martin Lown on the right to give you an idea where we are. So the green arrow tells us we're at very low shear stresses or shear rates in this sort of Newtonian regime that we call the low shear viscosity. So I'm plotting that low shear viscosity divided by the solvent viscosity that comes from the simulations. Those are the black spheres the black diamonds that are shown there. And they increase with volume fraction, as you see on the log scale there. What the simulations can do, though, is ask the question, how much of that shear viscosity comes from the Brownian motion interactions versus how much of the shear viscosity comes from the hydrodynamics? These are hard spheres, so they don't have any repulsions, they don't have any attractions, other than their hardcore repulsion. And what you could see is that at low volume fractions, the viscosity is dominated still by the hydrodynamics, but at high volume fractions, the Brownian motion, the packing of the particles into these cages, becomes more and more important. That's the blue curve. And the overall aggregate of those two lead to the overall viscosity. And the mode coupling theory that I talked about is the dashed line that goes pretty much through the suspension calculations for the suspension viscosity from simulation. For reference, that little blue line that goes to the 0 point is essentially the equation that's shown there for the relative viscosity -1. And that, you all remember, is probably the Einstein coefficient, the 2.5 that you see there, the first term on the expansion. And then the next term is the 5.9 phi squared. That holds at lower volume fractions, maybe up to 10%. From theory, that's the exact, if you will, equation for the shear viscosity of a colloidal hard sphere suspension. Now, we've done some work recently on trying to understand how that viscosity diverges and what theoretical law should best describe that. That's been published just this last year, some work with Bill Russell and Jan Mavis that appeared in the Journal of Rheology, and I've reproduced a few graphs from there. Now, there's a lot of experimental data. The left plot shows you the relative low shear viscosity of what we believe to be the best experimental hard sphere systems, where people have taken great care to try to determine accurately the viscosity, the volume fraction, and control the chemistry in a way so there aren't strong surface charges or strong van der Waals attractions. And you can see there's a lot of scatter in the data, despite the best attempts of many different investigators to measure this. I've also put that simulation data on the graph there as well. There are a number of theoretical lines, but the one that's important that really goes through the data the best is shown in the yellow box there. And that is the mode coupling theory, adapted a little bit to accurately represent the contribution of the Brownian viscosity terms to the overall viscosity. And what's plotted on the main graph is the overall viscosity, but just like the simulations, we can subtract off the hydrodynamic contribution, which I'll show you on the next slide, leaving only the Brownian contribution, and that's shown on the right graph. And you can see that Brownian viscosity contribution ranging over many, many orders of magnitude with volume fraction of the particles. And you can see the mode coupling theory, which is the dashed red line, goes through the data. You can read more about this in the paper if you want, but that simple theory that's shown above, which diverges with a power law exponent of minus 2.46, which comes from mode coupling theory, is the best of the various theories that we found to be able to represent the Brownian viscosity of hard spheres. The hydrodynamic part has been known for a number of years. This is the work of Rob Leinenberger and Bill Russell, published in around 2000 in the article that's referenced there. And you can see experimental data and the theoretical line, which is shown, the correlative line, which is shown in the yellow box there, which accurately describes the hydrodynamic contributions to the viscosity, again, the low shear viscosity of colloidal suspensions. Good. So if we know the low shear viscosity, then the next thing to want to know is how does the high shear viscosity for hard spheres depend on the volume fraction of the particles? Again, for reference, I've shown you that little plot from a small version of the plot we looked at from Martin Lown for the paint dispersions, and you see the green line there that indicates the high shear viscosity. We're looking at a viscosity before shear thickening, okay? Many suspensions, you might not see shear thickening if you don't go to high enough shear rates or if they have some stabilization on the surface. We'll talk about that briefly. That low shear viscosity has been correlated from experiment to diverge at a volume fraction of 0.71, and that's shown on the plot here, okay? And so there's a correlative line that seems to accurately describe I'm sorry, I misspoke. The relative high shear viscosity diverges at 0.71, and the accurate line that you see there, the model, is a reasonably accurate representation of the experimental data. Okay. Now, finally, let's look at the last part of Lown's data, which I find personally very interesting, which is the shear thickening phenomena. This, of course, is not something you want to see if you're trying to paint your house or coat paper, but might be interesting to devise novel materials for armor applications and other things that we've worked on. So where does shear thickening come about? Well, in the bottom yellow plot, what you see is some viscosity data taken on colloidal silica as a function of shear rate and volume fraction. You can see as I start off at the bottom, I have Newtonian viscosity that only weakly shear thickens, but you can see a very clear shear thickening transition at high shear rates. That seems to move to lower shear rates as I add more particles and eventually becomes discontinuous. That is, it doesn't reach a high shear plateau. Now, in the upper left, we see what happens at low shear rates, a cartoon, if you will, of what's going on in the suspension. I have colloidal spheres moving around by Brownian motion, and you can see the actual TEM of the particles shown in the lower left TEM there. If I force them to flow, I get shear thinning. The shear thinning is kind of like if you get in your car and you start driving on the highway. You start to follow the car in front of you, you can go much faster, as opposed to being in the parking lot where everyone's going in their own direction. You have to slow down and watch out for the other particles colliding with you. If I start to follow the particles in front of me, which is what happens when you shear a colloidal suspension, then you start to get the ability to flow more easily. The viscosity is less. But due to those hydrodynamic interactions, when particles are pushed very close together, they have something known as lubrication hydrodynamics, which is a very strong interaction that's operative in bearings and other mechanical devices. Is actually used to the benefit of being able to make a bearing, for example, in an automobile. But that causes particles to want to stick together effectively under flow. And that creates something called a hydrocluster type formation, which is shown on the blue particles in the rightmost graph up there. And if those start to become large, those hydroclusters, they can even bridge the suspension, and that could lead to almost a discontinuous increase in the stress, the very large shear thickening transition that you see at high shear rates. Okay, so what about this hydrocluster mechanism and the formation? Well, there's evidence from simulations. Here are some snapshots taken from the Cambridge group of John Melrose and Robin Ball. A number of years ago, they did some Stokesian dynamics-like simulations, and they just plotted out from their simulation box the particles that are involved in these high-stress events. And each one of these plots from the upper left to the lower right is essentially one strain unit apart. And what you can see are that the particles appear to cluster together under flow. Again, we're only looking at the particles that are involved in the high-stress regions of the flow that are forming these hydroclusters. And you can also see that they're not permanently stuck together, right? They come and go. Different regions of the fluid have the hydroclusters in them at any given time. So don't think of these as aggregates in the traditional aggregation sense. You turn off the flow, the suspension goes immediately back. Those flow curves that I showed you are completely reversible. And again, just to remind you, on the right is the simulation results that I showed you before, now plotted as a viscosity on a linear scale, so it's a little easier to see a logarithmic scale, so it's a little easier to see. And the red curve is the hydrodynamic part, and the overall black curve is the overall viscosity from the simulations, and the Brownian term are the open symbols. On the left is actually some experimental data taken in our laboratories at the University of Delaware a number of years ago by the graduate student John Vander, and you can see experimentally we see the same behavior for hard spheres. Again, the overall viscosity measured on a rheometer is the black circles. The blue triangles are the Brownian contribution to that viscosity, and the red squares are the hydrodynamic contribution. And you can see that the shear thickening, both for simulation and experiment, is driven by these hydrodynamic interactions. Again, everything there is reversible. There's no permanent aggregation. Finally, I want to show you, with regards to shear thickening, just a few other interesting things that you can look at. This is neutron scattering data, and we could talk about scattering at some later webinar and how we use that to measure properties of colloidal fluids. But for now, all you really need to know is that each one of those patterns that I show you were taken at a particular shear rate, using a technique known as neutron scattering. And they're devised in such a way that if there's no change in the structure, the pattern looks like the one on the lower left. Okay, there's basically no effect. But as I see changes in structure due to flow, that's what's being highlighted. And let me highlight the one in the upper right, which takes place in the strong shear thickening regime. And here you can see the red regions, red hot means more particles, if you will, or more scattering, which corresponds to more particles in the neighborhood. And the blue corresponds, the cold colors correspond to less particles. And you can see under flow that the neighborhood around a particle becomes very anisotropic, as the cartoon suggested, and that leads to these very high stresses. Particles are being driven close together and forming large-scale structures that are anisotropic under flow. That's the cartoon, essentially, again, moving from the low shear viscosity on the left, where the particles are nicely dispersed due to Brownian motion. Shear thinning, they form, essentially try to follow each other under flow. They don't have to form layers or strings, but they generally try to follow each other. And then finally, the formation of hydroclusters leads to a large increase in viscosity. Let me just compare some simulation data from John Brady's group, which are the grayed images in the center of the slide, for two states that actually have the same viscosity, roughly, but very different structures. And that viscosity comes from different reasons, okay? And the neutron scattering data you see on the lower left and the lower right corresponds nicely to what you see in the images that were published by the simulations, confirming the basic idea, which are in the cartoons to the left and right. So at the lower shear rates, we're in the shear thinning regime. Brownian motion is still very important and is an important contribution to the overall viscosity, and the particles are dispersed but roughly following each other along streamlines. On the right, you can see a very different structure that corresponds to these hydroclusters. Particles are pushed very close together, and the viscosity now is dominated not by the Brownian motion, but dominated by hydrodynamic interactions. So how you control that viscosity, that colloidal suspension rheology, depends differently in the different flow regimes. Even though the viscosity is the same, it's not the same colloidal interactions that are causing that viscosity. And again, just for reference, the simulations on the left and the experiments on the right confirming that. Oops, sorry, jumped ahead. So let's take a look at the properties of the shear thickened state. Both the cartoons and the theory that I've shown you suggest that we should reach a plateau viscosity, at least up to a certain volume fraction. We should be able to reach a certain viscosity. And that's shown in the upper right plot there, where I have different curves that correspond to the relative viscosity as a function of shear rate. And you can see as I increase the volume fraction, I get more shear thickening. This is a colloidal silica suspension like the one we've been looking at. And you get a plateau-like viscosity at high shear rates, or the evidence of that. The next two curves are the first and second normal stress differences. So for those of you who remember your rheological stress tensor, right, the viscosity is just one metric of a rheology of a material under flow. The other two that are important are the normal stress differences, N1 and N2. N1, for example, if it's positive for typical polymers, is what pushes plates apart or causes die swell in a material. And you can see that, first of all, these are plotted as minus N1 and minus N2. And they're fairly small on the big scheme of things. They're on the order of hundreds of pascals in the shear thickening regime, and they're negative. And they're about the same order of magnitude. That's very, very different than polymer systems where N1 is generally large and positive, right? So here you see the effects of hydrodynamic interactions show up as a large negative N1, okay? And that's been predicted from theory and seen in simulation and is shown here in experiment. Now, so what's going on? Well, you might think about these hydroclusters as no longer being Brownian particles, right? And just being large particles like we see in a non-Brownian suspension that are dominated by the hydrodynamic interactions between them, but they sort of trap the solvent in between. I've tried to capture that in that little cartoon on the left, where you can see the hydroclusters. I've drawn a sphere around them and sort of indicated that their effective volume fraction is that of the solids that are enclosed plus the trapped liquid in between. And so they have a higher effective volume fraction. And we can see that. What's plotted here is the relative viscosity that we measure. Those are the red stars for 5 different volume fractions in the shear thickened state, that is in that high shear plateau, plotted as a function of volume fraction divided by a maximum packing fraction. That maximum packing fraction that we find is about 0.54 for the shear thickened state. And that should be compared to what I showed you before as 0.71, which is the maximum volume fraction for the high shear viscosity, which is the same as what we would see in a non-Brownian non-colloidal suspension, okay? Now, for reference, I've shown you what we think to be the most relevant data from Singh and Knott experimental data on a non-colloidal suspension. Those are the half-filled symbols. And the black triangles are simulations of a non-Brownian system, okay, by Siru and Brady. And you can see that our data lines up with their data and lines up with the correlation line shown, the equation on the lower right, that describes that reasonably well. And that's been published by a student of mine, Colin Solonina, and myself in the Journal of Rheology just earlier this year. We could take then theories for colloidal, non-colloidal suspensions, such as that of Morris and Boulay, scaling laws, and we could apply them to both the simulations, the experimental data on suspensions, and our measurements for now the first normal stress difference and second normal stress difference that are normalized. That Greek symbol psi there, N, that you see, is N1 and N2 negative divided by the shear stress in the sample, so a dimensionless N1 and N2. And you can see that, again, the shear thickened state lines up very nicely with that of suspensions, non-Brownian suspensions, and follows the scaling law, which are the dashed lines shown there, and there are the coefficients we've determined and published there. So we now have a very good idea about the rheological properties of that shear thickened state. It looks like that of a non-Brownian suspension, maybe not so surprising. But the effective volume fraction of that state is much higher due to the trapped liquid in the hydroclusters. As a final tantalizing thing about some of the more recent work we've done on shear thickening is to look at the dynamic properties of shear thickening fluids. This is some work of a recent PhD student, Kate Gernon, who now works for GE up at the Research Center at Niskayuna in New York. And what Kate's showing you here on the upper left is the applied large amplitude oscillatory shear. So now we go beyond small amplitude to large amplitude, and we have a colloidal suspension in a rheometer, and you see the two curves there showing you the strain and the strain rate. The lower left curve, that you see as we're oscillating around, shows the stress, okay, that we're measuring on that colloidal suspension. You can see it's non-sinusoidal, as you might expect for a large amplitude oscillatory shear measurement. In the center of the plot, you see the classic three-dimensional Lissajous curve, that is, Lissajous-Bowditch diagram, which is stress versus strain and strain rate. And the black curve traces out in space and time, if you will, the behavior of the colloidal suspension. On the right, I've shown you the neutron scattering that Kate measures while we're doing that. And what you see, of course, is what I showed you before. The green means basically no change from equilibrium. The red means you have more scattering, corresponds to more particles being driven together by the flow, and the blue means less. And so we see the same type of structure that we saw under steady shear, but now, of course, we're changing the direction, right? We're oscillating back and forth, and if you watch that carefully, you can see the colloidal suspension hydroclusters flip back and forth with the applied rate of strain, as you might expect. Details of that will be published soon, hopefully, and are found in Kate's thesis. Finally, to mitigate shear thickening, you might worry about how do I get rid of it if you're worried about pumping a colloidal suspension or doing some coating with a colloidal suspension. And that's been worked out by some very nice calculations by John Brady and his students over the years, summarizing some of the articles there, where essentially I'm plotting a dimensionless viscosity versus shear rate, and the red curve that you see there is the behavior, theoretically predicted behavior for hard spheres. You have a low shear viscosity, shear thinning, it reaches just about a high shear plateau, and suddenly it starts to shear thicken, and it goes to a shear thickened viscosity that's actually higher than the low shear viscosity, and that's what we know. And as I add something like a polymer on the surface that prevents the particles from coming close together such that they can't form those hydroclusters, I can generally suppress that shear thickening, and you see each one of those curves eventually going down to the point where I never actually get shear thickening if I put enough stabilization on the particle surface such that I prevent the cores from overlapping. Now let's just talk briefly about the other interactions, right? We talked a little bit about the repulsion, and I'll talk about that. Another way to create stability in a colloidal system is to add electrostatic repulsion, right? We talked about that in some detail. Shown here is some experimental data from a PhD thesis of Frank Horn done with Walter Richtering in Germany and Norbert Willenbacher, who used to be at BASF at the time, now at Karlsruhe. And what you see here is zero shear viscosities, the solid symbols, for a colloidal latex suspension of polystyrene in water at different salt concentrations. So these are highly charged particles, and they repel each other. So the viscosity grows very rapidly. And as I go from the triangles to the circles to the squares, I'm adding more salt, and I'm screening out that behavior and headed towards the hard sphere behavior. But if I look vertically, let's say at 30% volume fraction, you can see that the triangles are orders of magnitude. The viscosity of that suspension is orders of magnitude higher than that of the squares, which I get by just adding a small amount of potassium chloride by screening out the electrostatics. On the other hand, I've also plotted the high frequency viscosity, which is the hydrodynamic component of the viscosity. And you can see that doesn't care about the electrostatic repulsion, right? That's just due to the presence of the hard core blocking the flow of the fluid. And the fluid flows right through that electrostatic area around the particles, so it doesn't care about the presence of the charge in the system. And so all of the suspensions have the same hydrodynamic viscosity, but there's an additional component now due to this electrostatic repulsion. We can actually scale that, and that's been done here by essentially taking an effective particle size that's larger and renormalizing, if you will, or effectively calculating a new volume fraction for the suspension that based on the size of that electrostatic double layer around the particles. That is, they're hard spheres, which is the core plus that double layer around it. And you could take all of the data that I showed you, plus data on many other systems, and put it all on a master curve, which you see there. And the solid line is what goes through the hard sphere data, and you can see that the electrostatic stabilized suspensions roughly follows that of an effective hard sphere. So here, stabilizing forces such as polymers or electrostatically stabilized colloids can be referenced back to the hard sphere behavior for the Brownian component of the viscosity, but the hydrodynamic component of the viscosity in this case is not affected by the presence of the electrostatics. Here's an example of steric stabilization. This is some work from the Leuven group, Jan Mavis and his students, where we plotted the relative zero shear viscosity for a wide variety of different systems with different polymer stabilizing layers and different particle sizes, and they all collapse down to a master curve. The variation in that viscosity is 6-7 orders of magnitude, which you would never be able to measure in the electrostatic or hard sphere systems, but the presence of that polymer layer makes them flow even at very low shear rates. You can get a zero shear viscosity even at such high values. That's well defined. And you could scale all of that data onto, again, the hard sphere-like correlation if you take an effective hard sphere size, which is illustrated in the cartoon in the upper left. Then moving on, we can see that we could summarize, if you will, what I've tried to tell you about today. First of all, we have both hydrodynamic and colloidal interactions that contribute to the viscosity, okay? And then different ways, and it depends on the nature of the colloids that you have. The Brownian motion that we talked about sets the time scale for the colloidal dispersion. It tells us at what frequencies or what shear rates or what stresses the system will know about it and be affected by the flow, where we're in the low shear regime or the high shear regime. And we can use hard spheres as a foundation for understanding stable systems and use the correlations that I've shown you to be either correlative of data or even maybe predictive if you know something about the polymer layer, for example, or the electrostatics on your system. There are other things that we didn't have time to talk about in this short webinar that you'll find in the longer short course or in the book, such as the effects of those attractions that we talked about, the formations of gels and flocks. This leads, of course, to something called thixotropy, which is a certain type of time dependence seen particularly in colloidal systems, as well as aging and other contributions to viscoelasticity. We didn't talk at all about particle shape or size polydispersity. We can also add electric and magnetic fields, so electrorheology and magnetorheology, which is often very important. There are a number of products colloidal suspensions that are used for products in those purposes. We could also change the media to start talking about colloids in viscoelastic media, nanocomposites. We could talk about microrheology of colloidal systems. We could talk about interfacial rheology of colloidal systems. What about capillary forces? What about friction particle surfaces? All of these are relevant topics that you'll see at, for example, the Society of Rheology meeting and the sessions, research ongoing there that's covered in various chapters of our book, and will be covered on the short course that is taking place in October at the Society of Rheology. So if you want to learn more about those, I'd encourage you to attend that short course. Thank you very much for your attention. Hopefully this gave you an introduction, if you will, to a very rich and I find exciting research area. And again, I'll be happy to answer any questions you might have.
Thank you, Norm. A recorded version of this webinar will be archived and available online through the TA Instruments website.